We'll be starting now.
Just can you give me 1 second, please? This is
Yeah,
was already...
I'll say a few words. Yeah, I'm just looking if there's anybody back there that wants to join us, but I don't think there is. Okay, so welcome to the last session of CIG 2017. This session is called Frameworks and Formalisms, and here we're going to look at, GVGA obviously is a framework, and we'll be talking about that a bit, but we'll also talk about some stuff which might become bigger frameworks for, future competitions and, might define research in the future. And also we'll talk about like some of the mathematical underpinnings of this work. Our first speaker is just about setting up, so quick information. This session is starting 15 minutes early, and on top of that, one of the speakers dropped out. So we're planning to be done by about 5 o'clock. So if you're hoping to, stick around here till 6, you might be sorely disappointed, and we'll have to leave this beautiful place earlier than you expected. There will be closing remarks afterwards, so maybe Julian will entertain us with like another, about an hour and a half long speech and dancing.
Yeah.
Okay. Oh, no worries.
Just give me
no worries.
A second. It was fine. I just had to restart it, my computer.
Yeah, quick reminder at this venture again. So if you're missing your CIG feeling already, you can go to Maastricht in a year, and maybe now is a good time to look around, identify the people you want to work with, get your paper going. Deadlines are approaching very, very fast. So it's always good to keep the ball rolling. Yes, and but more successful. Oh, I'm terrible at singing. You don't want to see me sing. Apart from that, what else? Is there any like last minute announcements we need to make? Hands up, who's coming to the CIG after party? Well, that's no. That's like yeah. Well, I guess I'll definitely be maybe sleeping for a bit. So.
Oh yeah. So this thing we haven't discussed.
So now what happened?
We're considering.
Can I see it on here?
Brilliant idea.
Okay.
Come up here.
Okay.
How about we collect people's slides and have them send us slides and put them on the program page next to the PDF to the papers?
Yes, we have actually gotten this request already from like the tutorial speakers. So very likely the tutorials will be available. But if you're interested, we should probably send that around.
We'll send a mail about that. So it would be completely optional, of course, but basically a possibility to send your slides and have us collect them and put them on, make them available to the wider world forever.
Yeah, and I think at that point maybe we should also include in the mail, the opportunity to give us some feedback. So if you want to, tell us how you liked CIG, either anonymous, so, get a Hotmail email, or tell us to our face via email. If you have some thoughts on it, we might be collecting these, and either we might be doing better conferences in the future. But if we get something, we'll probably also forward it to next year's organizers. So, I've already heard some people yesterday expressing the wish for some kind of industry track where it's maybe dedicatedly possible to submit that kind of papers, and maybe there's some more ideas that you have, and if you'll send them to us or the CIG governing body, which is what, Julian? Who's running?
The Games Technical Committee.
Yes, the Games Technical Committee is probably also very happy to hear your suggestions. And with that, I see we're set up. So without further ado, I'm going to introduce Gina Grossi, who's going to talk about evolved communication strategies and emergent behavior of multi-agents in a pursuit domain.
Thank you so much, and I apologize for that little bit of wait, but thank you. It's an honor to be here. So the presentation I'm going to do today is just part 1 or chapter 1 of my thesis for my master's degree. My supervisor, Dr. Brian Ross from Brock University, helped me create this work. So first I'm going to talk about the problem and go through some of the background research. a little bit about the system and the experimental details and the results in conclusion. And for more details can be found in my entire thesis from Brock there. So evolving cooperating multi-agent systems is a difficult problem, and it's been researched extensively through the years. A popular test bed for multi-agents is the predator-prey pursuit problem, or the pursuit domain. So the work that we have done adds to this previous work, investigating how genetic programs, or GPs, can be used in a predator-prey scenario to allow agents to learn to communicate.
Can you move the microphone closer to you?
Oh, sure, sorry.
And then we can get rid of some of the feedback.
Sure. Okay, so some of the research that we looked at is first a comprehensive survey of multi-agent systems. This was really beneficial to me in kind of understanding all the different terminology and definitions that are used in the various research papers that exist. We looked at coordinating agents in the pursuit domain and some research on communicating agents in the pursuit domain, and then looked at some papers with emergent behavior in GP, and then of course learning strategies in game environments. So our goal, again, is to investigate how GPs can influence learning using different communication protocols. So we looked at several communication protocols, and we want to task agents with learning the meaning of generic commands, and we want to define how well evolved predator agents can use a generic command language to learn the behavior of tracking prey. So we're looking at how we can develop a behavior. Now, there's many applications in the real world for multi-agent systems, specifically with robotics, any robots working together to complete a task. And I think there's a foundation for using learning algorithms, but specifically GP, in game development for creating game AI behaviors. I'm particularly interested in tool development for game AI, as my background is in game development. So limitations that we used for this research are the fact that the GP language is limited. We limited it purposely to allow high-level behaviors to emerge. Communication between the agents is synchronized, or basically linear, sequential. Messages are sent and received in a sequential order. And we use strongly typed GP to create the top-level GP structure. So here's an example of that. So this is an example of the GP structure that we used. We have the root node, of course, at the top level. And the second level contains the 4 agents. We have 4 predator agents. And then the level below that, each agent has 2 generic commands. And this is just in the part 1 of the study with 2 generic commands. So each of those commands are labeled C0 or C1, and they each are a subtree. Okay, so they represent a list of possible actions or behaviors. So our approach is to create a fully cooperative, heterogeneous team-based learning strategy with a global fitness. The heterogeneous team means that each agent develops its own subtree or evolves its own subtree. If we were to use a homogeneous team, that means all the agents would use the same subtree or same GP tree. We adopt a communication strategy using a learned language consisting of generic commands, C0 and C1. The generic commands mean that the agents have to give meaning to the commands itself. Where if we used a fixed language, then we would be predefining those commands. So we're using generic commands. We use the pursuit domain package. It's a package that allows you to set different parameters. So we chose a 20 by 20 grid, and it contains 4 predators and 1 prey. And if you look here on the screen, you can see that the predator is the orange triangle. It's not fancy stuff. I know we saw a lot of cool game environments, but this is just plain grid with 4 circles representing the predator agents. The agents can move up, down, left, and right, the predator agent as well. The agents also can stay. There's a field of view of 2 cells, and we call it an infinite grid because you can wrap around the edges, so there's no collisions at all. So if you go off on one side, you wrap around the opposite side. So the next 2 slides just describe the sending and receiving procedures. So each agent has its own message buffer. So an agent sends a message to other agents via a send expression, and the message contains message data. It also contains a command, in this case specifically a C1 command. And before sending, an agent will check to see if it is in field of view of the prey. If it is in field of the prey, then it gives directional information to the sender of the prey. So it says, hey, look, I can see the prey. Here's where it's at. On the receiving end of things, before an agent evaluates its own tree, it checks to see if it has a message in its message buffer. If it does, or if it doesn't have a message, then it by default evaluates C0. If it does have a message in its message buffer, it checks the command type, and then it will evaluate the specific tree associated with that command type. Again, in part 1 of this work, we only had C0 and C1. So if it also has a message, what it does is it takes the message and it updates what we call an LRM node, which is a last received message node. It's just a terminal node in the tree that it can use for information about the direction of the prey. So here's an example of the system overview using the message buffer system and kind of describing how the system works. In this case, it's taken from the part 2 where we used an additional command, so you see a C2 in there as well. But generally the process is the same. So in this case here, step 1, agent 2 is sending a message and it has a message a container, and it has the ID of the sender of who it's sending to. And it has a message type of C1, sending a C1 command in this case, with message data. And all it does is just send a message, it gets into the message buffer of agent 1. In step 2, before evaluating the subtree for itself, agent 1, it updates the LRM node there. You see an LRM node with the message data. It doesn't know what that information is, it's just getting the information and updating its node. And then finally, step 3, it checks the command type. In this case, it has a C1, so it evaluates its C1 command branch. So just talking a little bit about the fitness structure, the fitness measure is based heavily on the environment itself. So we describe a cycle as being one time unit and one movement step on the grid. We have episodes, which is equal to 30 cycles, and that gives the maximum time that an agent can learn to track prey. And the green areas represent, I'm not sure if you can see it there on the slides, but there's green lines there representing the starting areas for each agent. An agent will always start in its own starting area, but at a random position. And the details of training, each training run consists of 10 episodes. At the beginning of each episode, it gets a new starting position. And then with testing, works the same way, except you get 30 episodes and actually get the same starting position. The fitness measure is quite simple. It's just the total distance of the agents to the prey for all cycles and for all episodes. And so GP individuals with better fitness scores will minimize this distance sum to the agents. So here's the equation for the training, and below that we see the equation for testing. Testing is 30 episodes, and we just take the average of the total distance as the fitness for that test. We use typical GP parameters. The generations, 125 generations. Crossover rate is 90%. Mutation rate is 10%, and we use 20 runs per experiment. So the communication protocols that we use, we tested 7 different communication protocols, and the protocol just means how, well, the set of rules that the agents use to send messages. So how are they defined? So I'll describe just 2 of them because we have 7 here. So the first one is send 2-2, and that basically divides the 4 predator agents into 2 teams. So and the teams can communicate only with each other. So agent 0 and agent 1 are in one team, and they communicate back and forth with each other. Agent 2 and agent 3 are in another team, and they communicate back and forth with each other. Another example is a send all communication type, and that's more like a broadcasting system where one agent will send a message to all other agents. So we have messages flying all over the place in that case. There's 2 experiments that were performed, one with linear movement of the prey and one with random movement of the prey. So with linear movement of the prey, again, it's simple. The prey starts in a random area, a random position in its own area, and then it moves in a linear pattern up, so north. And with the results, we found that the send all and send 22 experiments were almost exactly the same. They were off by 1 with their average fitness of 20 runs, and they were found to be significantly different using a 95% confidence interval with the worst performer send K. But the ones in the middle, the bands in the middle, they showed to be equally they performed equally as well as each other. So most tests involves competent agents that were able to follow the prey. Many communication protocols, as I just said, did not produce significantly different results. There was a few of them that were just kind of all similar. But what was interesting is some of the the top performers performed or showed high levels of coordination among agents, and I'll talk about two of them. One specifically was a synchronization of message sending that caused a staircase pattern that allowed the agents to find and then follow the prey. So this was found in two different protocols, the send all protocol. And in this diagram here, we see a staircase pattern with the agent, this is agent 1, the purple agent. And then in the next one was with the send 22 protocol. And we see agent 3, the green agent, moving in a staircase pattern. Now this looks pretty simple. What was interesting about this is the fact that the staircase pattern is happening, or it emerged on its own, and it's happening because of this message sending. It's an alternate message sending pattern that exists. And I'll try to describe that in this next set of slides. So on the upper right-hand corner, we see the GP tree for agent 1, the agent that's moving in a staircase pattern, the purple agent. On the bottom right-hand of the screen, we see the message buffers for each of the agents. And what we found is that from cycles 9 to 13 in the runs, or the test run, was that agent 1 and agent 3, they send messages to each other every other frame. So this results them processing or evaluating their C0 and C1 branch every other cycle. So here the boxes in yellow show agent 1 has a message in its message buffer only in cycles 10 and cycles 12. So every other cycle, these are just snippets of the message buffer, but it continues through the entire the entire run. And then if we notice in the C0 branch, it has a down position, and so it moves the agent down. And then in the C right position, it moves the agent. C1 position, it moves the agent right. So what's happening every cycle, cycle 9, agent 1 has no message, so it evaluates C0, moves down. C10, it has a message, it evaluates C1, moves right, and it continues this in a staircase pattern until it finds the prey, and then it follows the prey. So here's a video kind of that. In the first case, just keep an eye on the staircase, the purple agent. There, it's just out of view of the prey, so it doesn't follow it. Here, restarting. In that case, it gets in view of the prey and starts following the prey. So this was using a very simple GP, so it's interesting that the message sending, that pattern, that alternate pattern, happened in the different protocols. Another example that showed some high level of coordination, and I think this is what's interesting specifically to me that I found, was the fact of we found a guard reinforcement behavior. So if you think about a game like Metal Gear Solid, if you're familiar with that game, what happens is a guard stays in an area and protects an area, and then when he spots an intruder, he notifies the other guards and they come running and they all follow and attack the prey, or sorry, the intruder. So here's an example of that. If you're not familiar with that, here we see, this is an old version from the GameCube. We see a guard protecting an area. We see Snake, the intruder, come into that area. And then you'll see that the guard here on the upper right-hand screen, he hears something, turns red. That means he hears something and goes into that area. But he's not notifying anyone yet because he's just hearing it. And then next, it's like there, that guard there saw the intruder and alerts the other guards, and they come running, they follow it, and they attack the prey, but continue to follow it. So that behavior did evolve using a very simple GP language in send all run 15. Now it's very, very basic, but if you were to code it or script it, it would be something very similar. So here in the upper right-hand corner, we see a GP structure for agent 2. Agent 2 is a dark blue agent, and he acts as the guard. He basically stays, if you look at his GP tree, the if dist expression there just represents if I'm in field of view. So if he's not in field of view, he basically stays. If he is in field of view, he sends out not one, but 4 messages. And he basically floods the agent's message buffers with directional information to the prey. And you can see that with the highlighted rectangles or squares in their message buffers. So they're getting a message from agent 2 with directional information to the prey. So that's what that diagram shows. So he's basically saying, hey, I just saw the prey. Here he is. Now, what's even, I think, is more interesting is that the actual agents use that information. So they're able to, well, one of the agents specifically, the purple agent, again, agent 1. You can see here in agent 1, he's generally moving from left to right across the screen. And then when he starts evaluating and getting messages from agent 2, he turns back and moves in the direction of the prey. And you'll see in the video that he kind of hovers in that area until he is in view of the prey, and then he follows the prey. So we'll see that in the next slide. So if you keep an eye on, this run shows a couple of cycles or a couple of episodes. So if you keep your eye on the dark blue agent, you'll see that it stays in position, and then when it's in view of the prey, you'll see the purple agent on the bottom kind of moving back and forth. So he's staying, and that one, and there he's in view, now he's moving, and the purple agent kind of just, it's very, very subtle, and yes, very simple, but if you look at the message buffers, you can see that it's actually using information that it's getting from the guard agent. So the next experiment that we did was with random movement prey. So in this case, it's exactly the same experiment as a linear movement, the linear movement prey experiment. And what we found here was that the results were all very similar. There wasn't a significant difference in the results. Although send all was the best and send 22 this time was the worst, there still wasn't a significant difference in them. So again, the pattern of the alternate message sending pattern, that did appear in this as well. So it's emergent behavior that also appeared in the random movement experiment. So if you look at their message buffers, the agents did have messages in their message buffer every other cycle. However, because the unpredictability of the prey, its movement, it really didn't help the learning there. So the agents, in some of the cases, were able to move in the direction of the prey in about 2 directions of the prey. So we're able to follow and move it as it moved randomly in 2 of the directions, but not all 4 directions. So what we found is that we need an enhanced GP language to allow agents to learn to follow the prey in all 4 directions. So in conclusion, what we found that we did find specialized agents, and they were common. But generally powerful agents did not evolve. So we can say, here, there's a general solution for everything. We didn't find that. Some experiments did regularly evolve interesting behaviors that show high levels of coordination. So we described that with the emergent behaviors of the synchronized message sending and also of the guard and reinforcement behaviors. And then we also found that this synchronized message sending did occur in the random movement of the prey, but it wasn't as successful. So in future work, we are going to expand the GP language and fitness for random movement prey. And we're going to test solutions in alternative predator-prey scenarios. For example, the Ms. Pac-Man tested in a real game environment, and test the solution. And this is needed to test a solution in different variants of the pursuit domain. I think increasing the grid size will help with the fact that some of the protocols performed equally as well. I think that hopefully we'll see different results in the different communication protocols. As continuing with my work, we did find, we did expand the GP language, and what was happening in this case is, again, we're having emergent behavior, but what I think, again, is interesting is the fact that the agents themselves are dividing themselves up into sender and receivers. So we have a sender agent and a receiver agent, and the sending agent is able to apply specific meaning to a command, like it actually decides when to send a command and what data to send with it. And receiving agents are able to understand or interpret the meaning of the sender. And we have tested just very, very briefly in not the Ms. Pac-Man game itself, but the Pac-Man environment. So one mode of the Pac-Man environment where the agents chase, then chase mode basically. And we found similar results to the expanded GP language, but only in segments of the different cycles. And that is because, as we expected, the agents have issues moving around collisions because our fitness function in this case does not account for collisions. And that is because we just wanted to test our solution to see, okay, let's just try it in an environment with collisions or an environment that is used for a particular game. Let's just see what happens. And we knew it was going to be perfect, but we just wanted to see what would come of that. So we know that there needs to be more work with that. So I think that brings me to the end. I just again want to thank you for being here. And if you have any questions, please ask.
Are there any questions? Or in this case, I would actually be curious, how did the agents you did the the agents you were looking at actually have some form of internal model to kind of determine where the prey they were looking for is, or kind of help them search the prey?
No, so the only thing that they had was that information from if they received a message, that information, they had one node, one goal node, that if they were close within, like if they were in field of view of the prey, that goal node would have directional information to the prey saying, hey, this is the prey, so you go towards it. So on their own, if they found the prey on their own without any message in their buffer, they could follow the prey if they stayed in view of the prey. So they could do it on their own, if that's what you mean by internal data.
Well, I mean, so you could, for example, enhance a predator-prey model like this by having a richer stock of, like, internal knowledge of maybe where you've looked, or
Right,
you can have like some kind of behavioral model of the prey and go like, okay, I haven't seen it here, so let's look there, and then you might not go back, but go somewhere else.
Right, we didn't. We just started off with just a simple language to kind of see what types of behaviors would emerge, and with a goal of let's learn the behavior of tracking the prey first and kind of see what's happened. So it was just vanilla. It was not did not have any.
Because I could imagine that with the way you look at it here, the message buffers could actually be used to have some kind of communal memory, because you could
Yeah.
use this information around and kind of maintain it by kind of exchanging it between yourself.
Yeah, the message buffers were encoded in such a way that you could apply whatever data in there. So we just started with a vector, 2D vector information to the prey, but you could easily add more information, which is really something to look into. It's a good idea.
Oh, okay.
These things not working?
So I mean, just comments on domain. So basically, I mean, it's cool work, and I think, I mean, we've seen a lot of evolution of communication work in evolution robotics, where, I mean, Floriano's work and so on, and some of the, the swarm bots and swarmonoid projects. And I've always felt like, the environments are too simple. They have too few things to communicate about, essentially. There's nothing to talk about here. So, I mean, and I think it's cool to look into other environments as well. So geometry friends, which usually a competition is run about at CIG, is another interesting thing. We have two agents. They need to communicate about how to clear a level and get from place to place. And that would be really interesting to see if that you could have emergent communication in that setting. It's a little bit like a very simplified version of the two-player mode of Portal 2, for example. And other sort of, I mean, there's a Dota 2 framework.
Okay, I've just learned about that here, so
exactly.
yeah, I'm learning a lot just being here.
And it's the coordination part, I mean, between the multiple agents that's really interesting. And you want to be able to see if you can have them incrementally, for example, learn to talk about one thing and then another thing and then a third thing,
Yeah, so we just started off with the commands being very, very simple to see, okay, what can happen? And those, because they're generic, you can apply, as your GP language is enriched, they can apply more meaning to it. And again, with the data, as Christoph said, adding more data to it, so I do find it, I do find it's interesting, especially adding more things to the environment and how they react to the environment. And I think that's just because of having a gaming background or game development background, just like how would we use this, and that's where I'm coming from. Yeah,
I think MOBAs is like a fantastic sort of, MOBAs like Dota would be very good. Sort of.
MOBAs, Dota. Okay, I'll write that down.
Okay, thanks.
Okay, thank you.
There maybe one more question, but could I ask the next speaker to set up their laptop?
Oh yeah, I already have it undone, so yes.
Hi, thanks for the talk. That was great. A much simpler question was, I may have missed it, so it's possible. Did you try running a baseline just with no communication?
Yeah, we did that at the beginning, and our goal is to kind of just look at what happened, because they can find the prey easily without communication. That wasn't the question that we were looking at. We wanted to see how they could. We were looking at communication to see how the different protocols would work and how they would learn language, the command languages.
Yeah, oh no, absolutely. But it's just curious to see the difference between none versus the communication tool, especially as you start changing the environment, because then it's what because as you said, in the small environment maybe it's less pronounced, whereas in the large environment you'd expect communication to become increasingly important. It'd be quite nice to see that difference. So that's just my comment.
Expand the grid. And one of the research, I think Eva one of the very first, not
Yeah.
the first, but that put communication, also realized too that as you communication is great farther away, but as you come closer, as you find the prey, get closer to the prey, then there's a cost to it. It's not needed. So yeah.
Okay.
Yeah.
No, thank you. That's great.
Thank you.
Is this your water?
I think so. Okay, thank you.
Well, thanks to our speaker, Gina Grossi. Our next speaker will talk to us about the Showdown AI competition, which I believe is named so because for legal reasons they couldn't use the word Pokemon. So you haven't heard that. I didn't say that. The work will be presented by Scott Lee, and he worked together with some foreign author, Julian to Galius, I believe. So Scott, take it away.
Okay, good afternoon, everyone. Thanks for coming. I'm Scott. I'm a master's student here at NYU Tandon, and I'm here to talk to you today about the Showdown AI competition. I'm going to start by going a little bit over what Pokemon is as a game, some information about the framework, the unique challenges it presents to AI, and very briefly how agents perform in this game. So the natural question here is why Pokemon? What makes it interesting as an AI competition? In addition to the unique challenges that it presents as a modern game, it also is very well known and has a well-established metagame that makes it easy for us to compare the performance of our AIs against the performance of people without really having to do too much work in trying to get people interested in our game. It also does really nicely in bridging a gap between the current state of turn-based AIs in Go and chess and real-time strategy games that we're all interested in, like StarCraft. It has several features that are prominent in both of those games, and in doing well in Pokemon, I think that a lot of those techniques will transmit nicely to both ends of the spectrum. So Pokemon as a game, for those of you who aren't familiar, is a turn-based game in which two players attempt to defeat each other's teams. The game is largely symmetric in that both players have access to the same sets of Pokemon, and their probabilities of winning are largely equal before they start building teams. Because of this game has a very strong deck building component in which preparation before the actual game is a key part of victory. This game also features stochasticity, a decent amount of randomness, and a great deal of hidden information which acts as a key component to strategic depth. To explain it a little better, here's a brief video of people playing Pokemon. So what you can see here is that you have two sides. One of them has one Pokemon, the other has another Pokemon. Now, both sides have 6 Pokemon, so they're free to switch between them on their turn or use an attack instead. A Pokemon is considered fainted when their HP runs out, and until their HP runs out, they're free to continue attacking. Now, the game has evolved quite a bit in recent years, and there are a number of moves in addition to dealing just damage that can also remove things like items and cause status effects and change stats. And the metagame has evolved greatly around using not just the conventional strategy of straight up attacking, but also exploiting various strategic elements that it has. The competition itself makes use of what's called Pokemon Showdown. Pokemon Showdown was the thing that you just saw in the video. It's an online website where players come together to battle one another. It's fairly popular. It has thousands of users at any given time, and it is open source. We essentially use the engine source code, added our own interface layer so that the agents could play the game, and everything works okay from there. It uses the Generation 6 standard. For those of you who are familiar with the series, that is X, Y, Omega Ruby, and Alpha Sapphire. Those are games that were released within the last 3 years, so they're fairly recent, although they're not the most recent games. Additionally, the competition gives both agents random teams. In this way, we can actually sort of test the generality of agent performance. By giving them many, many different teams that are generated at random, we can see how they perform in general against other agents rather than specific strategies. Now, as I said earlier, hidden information is a key component of Pokemon. It influences a lot of the decision making. One key aspect is that the 6 Pokemon that our opponent has are not immediately given to us. This actually makes simulation to the end of a game incredibly challenging because we have no idea what options our opponent has. Additionally, there's a decent amount of hidden information in a Pokemon's stats, and that sort of thing determines how much damage you're going to do, take, and turn order, meaning that there are very few guarantees when you make assumptions in a forward model or in a random rollouts for MCTS type algorithms. Now, there are a number of ways to deal with this. The information is revealed to a player as it happens, meaning that a system can actually take in that information and augment its own understanding of the game state as this information becomes available. However, because even as it becomes available to us, we don't know everything about it, there is a certain gap in which an effective agent is going to have to make assumptions about what their opponent is using. Now, it's perfectly possible that you could exhaustively explore every possibility of what your opponent looks like, but the space is incredibly large. Pokemon can learn any of up to around 80 moves. There are a lot of Pokemon in existence, and stats are essentially a continuous variable, making it incredibly impractical to explore every possible configuration. Now, the branching factor of this game, for those who are interested in state-based tree search for this approach, for this game, is typically around 9 or 10. You have 4 moves at the top, and you can switch to any of 6 Pokemon, well, 5 Pokemon, because one of them is already out. Subtracting, of course, anything that you might get locked out of over the course of the game. The issue here is that although your branching factor is quantitatively consistent, qualitatively it changes quite a bit over the course of the game. In games like Pac-Man, it makes sense. Up, down, left, and right are your 4 moves, and each of those 4 moves are self-consistent over the course of the game. Whenever you hit up, it's always up. However, in a game like Pokemon, when you say you use the first move, that first move can mean a lot of different things. There's a lot of semantic significance to each individual move, and it's incredibly fluid, which makes it challenging to conceptualize what moves you have, even though it's easy to tell how many moves you or your opponent have. Now, one thing that sets Pokemon as a turn-based game apart from other more traditional turn-based games like chess or Go, and also from some modern games like Hearthstone, is the way it processes turns. When we think about how Hearthstone and chess process turns, we think of it as I make a move, my opponent makes a move, then I make my move, then my opponent makes a move. Now, when you talk about real-time strategy games, the paradigm is different. Both players make moves largely simultaneously, and the system processes them simultaneously in a single frame. And Pokemon processes its turns slightly closer to the way real-time strategy games do. What it does is, at the beginning of each turn, both players are asked to make a move, and the game decides, based on various numbers and systems, how to process both of them atomically. This introduces an interesting problem in which an agent's moves can actually get preempted. What they choose to do actually has a possibility of failure if their opponent has a higher priority than them and they are interrupted. It also creates a problem in which an agent, the game state that an agent is given at the beginning of the turn is not necessarily the one that they're going to get when their action comes up, meaning that an effective agent is going to need to be able to account for unreliability in their given game states. Additionally, even if your agent is aware of the priority that your opponent has, this priority can actually be overridden by various moves, which means that even if you know that your opponent will go first in the next round, you actually have methods of going first instead, which again creates that much more uncertainty in the system. In terms of game depth, for systems that intend to simulate to the end of games, it's important that a game is finite because you can't simulate to the end of an infinite system. Now, Pokemon has systems in place to punish artificial and malevolent infinite loops. There are systems that say if you try to create an infinite loop artificially, you automatically lose the game. However, it doesn't account for the possibility that infinite loops can in fact happen organically, and if both players think too simplistically, it does actually happen. Now, I'm going to give you a toy example in which we have player 1 and player 2. Now, let's say that both players are acting strictly greedily. They're going to use only the most damaging move they have access to, and if that move belongs to another Pokemon, they will spend their turn switching to that Pokemon to use that move. Now, what happens on turn 1 is that we have player 1 with an Alakazam and player 2 with a Steelix, and both of them decide that they can deal more damage by switching to a different Pokemon. However, because of turn atomicity, we can't change our minds once we make it, and so at the beginning of turn 2, we find that both players have switched their Pokemon, and now both of their moves are suboptimal. Now, looking at this again, both players will again decide to switch Pokemon back to their originals because they decide they can do more damage this way, and what we end up with is the same state we began with. And because of our highly simplistic, predictable, and deterministic agents, we're just going to end up infinitely looping between these two switches without really a mechanism for punishing either of them because essentially both are at fault. Now for systems like these, the competition defaults to a tie, but the ability to avoid the situations altogether would have been better. Now, this game also prominently features deception. You can think of it as a special kind of hidden information in which rather than having the game state not have a field set, the game state actively lies to our agents. So Zoroark is a unique Pokemon that was introduced in Generation 6, and its ability basically allows it to disguise itself as another Pokemon when it's sent in. What this means is that our agents are under the impression that our opponent is a specific Pokemon. That is not true, and when we try to make moves, a contradiction will occur. If an agent isn't capable of processing these contradictions, then it might continue to make moves infinitely into futility, essentially, because it's doing things that are clearly not effective against the Pokemon that is hidden. Now, this creates an interesting problem in which we have to also have agents that are capable of attributing contradictions to their root causes. Because of how much hidden information Pokemon features, it's actually non-trivial to see something go wrong and then decide this is the reason that this went wrong. And this is a unique challenge that is pretty prevalent in a lot of modern games, the ability to see something went wrong and know why it went wrong. Additionally, when we talk about more those greedy type agents, they need a method of evaluating states. And Pokemon as a whole features a lot of, I suppose you call it, delayed gratification systems. A lot of the moves that you have don't pay off until much later, and a lot of the statuses that are prevalent in a game state are by and large categorical. There are a lot of strings and not easy to quantify. This creates some interesting problems for things like A-star and those types of greedy algorithms. Now, there's also the ability to disable an opponent's moves, which you don't know about, and again, the quantification there is difficult. The ability to integrate domain knowledge then becomes key in evaluating a game state. However, again, that is non-trivial. So I'm going to talk briefly about the sample agents that we had for this competition, just to demonstrate that the framework works, and so we can see how different algorithms perform. So our basic tree search algorithms, our breadth first search, our depth first search, only consider the fainting of the current opponent's Pokemon as the termination condition for the search. This is in part because the game run tends to run very long for all 6 Pokemon, and also because once the current Pokemon faints, it's incredibly difficult to predict what's going to happen afterward. And it also, the evaluation method for the algorithms we implemented, like A-star, put multipliers on different things to assign value. These are pretty arbitrary things, and in general, the tree search algorithms out of the box don't perform particularly well. They need a great deal of enrichment to actually perform. Strategic AIs, ones that are built almost entirely on domain knowledge, like if this, then that, if this situation, then make this reaction, generally perform reasonably well. They play very much how basic human players would play in Pokemon. It captures effectively the strategies of maintain type advantage, use the most damaging move, and that works reasonably in low-level play, which is about as far as our agents managed to get for the time being. Now, we also experimented with integrating domain knowledge into some of our tree search algorithms to do things like move ordering and aggressive pruning, and we find that those actually perform pretty well, but at the end of it all, the strategic AI and domain knowledge enriched agents perform roughly equally to each other. If you want the specific numbers and implementation details, you are welcome to refer to our paper. Now, this of course leads me to future work. We did have our first run of the competition this year, and what we found is that there were 2 agents that performed roughly equal to each other. Again, one strategic rule-based agent, and one that uses domain knowledge to enrich tree search. This year, because we gave both players random teams, we couldn't really capture some of the strategic depth that Pokemon has. In the future, we would like to move into also giving agents the opportunity to build their own teams. Also, later in the lifespan of the game, double battles were introduced, in which 2 Pokemon battle on each side, and that actually introduced a lot of strategies and synergies that were interesting to exploit and might be interesting to see how agents perform in. We use Generation 6 rather than Generation 7, which does introduce new mechanics, and we would like to integrate those. And we would eventually like to validate our agents against humans. One of the key benefits of using Pokemon as an AI benchmark is that it's incredibly easy for us to connect to, say, the Pokemon Showdown servers and essentially release our agents into the wild and see how they perform organically against players who might not necessarily know they're playing against agents. And that's all I have to say on the matter. I'd be happy to take any questions now. Thank you all for listening.
Would you like to come up to this microphone?
Yes, of course. Okay. So first of all, you didn't mention that, but I remember from the paper this Pokemon that do magic is forbidden. Like you simplify the work for the agents. Yeah, you don't use this. I mean, this Pokemon that can hide.
Oh, yes.
You didn't mention that. Yeah,
we did end up banning that for the competition. That was mostly an engineering issue. It's having the canonical game state lie to our agents created some awkward problems in asking the agent for decisions.
You also mentioned like kind of a constant branching factor, which means there's no items and stuff like that to use by the players, which I remember there were in the first
yes.
Pokemon games I played years ago.
Sure. So
there's no like that.
Items are predominantly triggered effects, so you can't actively use them. And in competitive games, items are forbidden. You don't have anything other than held items.
So the last thing I would think it will be nice if you won't rush with adding new stuff for the so new competition and wait until some kind of level will establish, because it's fairly new and people need to catch up with what's already here to have this challenge. So
sure. Yeah.
I mean, just to perhaps potentially contradict. Generally, I very much agree what you say. Don't add more complexity until you competitors have learned to get somewhere with the current status. However, being able to choose your own team might actually make it easier to develop a decent agent.
I mean, yes,
yes,
but if I had about doubling the...
No. Yeah.
No,
that's true.
When I say future work, I mean like pretty far into the future work.
So, I mean, a follow-up question to that. I mean, for somebody in the audience is interested, I mean, are there any plans for running a follow-up competition, and where would this likely be, or where could people find like information about this?
Sure. Okay. So, I do hope to run the competition again with some major overhauls to the framework. There were a lot of imperfections with how it was implemented, and so it does need a lot of work. That being said, the framework itself is open source, and it does connect to the Pokemon Showdown server. So if you want to play around with it, that's fine. As for where, yes, somewhere on the internet is a good idea. I haven't really thought that far ahead. Yeah, fingers crossed. But yes, there are plans to improve and continue running the competition.
And basically, I think the things you outlined in the beginning, the hidden information and the ability to have deception, would you say these are the main selling points that this competition, let's say, apart from like the other, because this year we saw like about 15 competitions, I think, in CIG. So basically by adding this, I mean, one of the questions that naturally arises, like, what's a new type of like challenge in this particular competition that we also, should run this? Are those the ones, did I identify them correctly? Is there other things that set this particular competition apart?
I would think that deception and contradiction are the key contributions that Pokemon brings to the AI competition space. when we think about modern like games today, a lot of them are like unreliable game states, right? Like players don't have not even perfect information, but like completely reliable information about what their states look like. And what we see in a lot of competitions is that the states are very reliable, and that's an important thing and a very useful thing in a framework, but not something that necessarily holds in the wild.
Or reality.
Yes.
Okay, are there any other questions for Scott? Well, in that case, I would like to thank our speakers. Thank you very much, Scott. And I would like to ask our next speaker up, a man who needs no more introduction at this. I believe you might have seen him before, either in the tutorial he ran or in the 1 to 5 papers I believe he was involved with. So I believe this talk will be about how general video game playing escapes the no free lunch theorem. Oh yeah, I did remember that correctly. Which I guess is an interesting topic to bring up, as I've actually very, very recently read an article online where somebody says that the free lunch theorem will be one of the big stumble blocks for AI that they will be unable to overcome, and maybe we will not get, the glorious AI overlords in the future because of that. And maybe you can tell us that with the GPGI framework, this might happen after all. So. Or not, I don't know what the answer is, so we'll see from your talk. Diego Perez Libiana.
Thank
with
you.
Dan Ashlock.
And with Dan Ashlock, who is not here. Essentially this is a vision paper that was submitted with Daniel Ashlock and also in a joint work with Amanda Saunders, who's a master student of Diane. This presentation was going to be pair presented with Daniel, who had to leave Decathlon because of scheduling issues. So basically, I'm presenting both parts. The idea of this paper is essentially saying, we have seen actually during this conference that there are many algorithms, many different approaches to try to solve and play general video game AI. And in general, what happens is that there is no algorithm that is able to win in all cases. There's no algorithm that is able to or some modifications of the algorithm. Nothing is really dominates over all the other things. And possibly, and that's the main point of the paper. One of the points of the paper is that there is an error trying to think that this is going against, because the authors have been ignoring the no freelance theorem. And the claim that we're making is that actually, if we choose general wise enough, we shouldn't worry about the no freelance theorem. So we're going to explore that and also talk about the actual a system to actually learn how to classify games. So just in case nobody or somebody here doesn't know what the no freelance theorem is, essentially what it says is that no optimizer that fails to resample fitness cases is better than any other on average over the space of all problem. Which basically means what I said before. You can create an algorithm that is able to beat or dominate all of the algorithms in all problems. So this was proposed in this paper in 1997. At that time, I was still in high school, so I couldn't really value what this initial reaction was. So I'm just going to say whatever Daniel was thinking about this. Yes. So the initial reaction apparently was people didn't like that, because it was a moment where everybody was creating their own problems and creating the algorithms to solve those problems. And that was kind of a controversial idea. Although after a few years, or maybe at the end of the same year, this theorem was actually accepted and it even won best paper awards. So, well, if this could maybe sound too dramatic, but actually there are some reasons why you shouldn't worry about the free lunch problem. One of them is that, well, essentially, if you think about the theorem, what it's basically saying is that you can just take one particular domain and specialize any algorithm or one algorithm in particular, and then be the best one, basically dominate that particular. And that's good because that solves specific problems. and allows you to work and make and write publications, write papers. So that's something good for us. Then there was this initial hype, which I didn't see either, that evolution algorithms were thought to be a Swiss Army algorithm in the sense that they could basically solve anything, which was utterly not true, because for evolution there must be some characteristics in the problem itself to work, like the fact that the fitness must be inheritable from one solution or from the parents to the children, which is an assumption that excludes almost all optimization problems. And then the space of all problems itself is something that has to be taken with care, because if you think about all the possible problems, one of the important points here is that you assume that, or at least the problems that we are interested in, assume that when you have a space search, a search space with different points, points near those points in the search space should have a fitness that is more or less close to this kind of continuity in the search space and in the fitness space. And actually, if you think about any other problems, especially in combinatorial optimization problems, some of them are actually not like that. In the particular case of games, when you think about optimization problems, there's enough room to actually prove this theorem. And what we claim is for the game plane is actually quite harder to know. It's more difficult to actually define this no free lunch theorem, mainly because it's a more complex environment. You have, in case you have 2-player or even n-player games, what you have is that you have another agent that is continually changing, continually moving, and in fact what it's doing is basically changing the way you have to play, they have to evaluate different solutions. So then if you have all the games, you can try to identify which is the actual subdomain or a subgroup of games that you can work with. For instance, I, in this case is Daniel, is claiming that it's possible to prove a no freelance theorem in case of games like the divided dollar or the prisoner's dilemma. And the point is, it depends on how much do you want to specify the games that you want to use in this particular case. And what we want to do is actually care about the games that we really are interested in. So if, for those of you that were in the tutorial on Tuesday, one of the things that we were showing is that, that were not in the tutorial, was that we can vary the algorithms and the parameter values of the games, and essentially just let's say that we play aliens, and then what we do is modify all the values. Say modify the speed at which the aliens move, the probability that they can shoot, the number of aliens, and if you just do that randomly and try to play the game, those games are totally not interesting. They are basically impossible to play, and we really don't care about a game or an algorithm that tries to beat a game that is not interesting, is not fun. Similar with the games generated in the rule generation competition that Ahmed was presenting before, and Mike. So there are many games that we actually don't care about. And then if what we do is we only care about the games that we really are interested in, they are fun, or they actually look like games. In that case, the algorithm that tries to be general enough to play all those is actually quite specified if you relate it to the vast amount of games that you can have. So the GVGAI framework, or I could call it project with all the things that it has, essentially what it does is actually focusing on games that anyway we'll ever care about. It's doing games like Pac-Man, it's doing games like Aliens. Camel Race has a little bit of bad publicity, but after all, it's just a race. It's getting as fast as you can to the end of the line. So they are games that actually we care about. And we're actually proposing this in several ways. One way should be obviously the planning track. We've talked about this before, single or 2-player planning track, where the objective is to generate an agent that can play with the user forward model, trying to win, doing games at one shot. Basically, you drop the agent in the game and tries to win the game and score as high as possible. Or the learning track, when you don't have the forward model, and when you have this repetition, you have the agent plays continuously the same level multiple times, various level, learns how the game is, or is supposed to learn how the game is, and then is tested in different levels. We have level generation track or rule generation track that generates what is asking you to generate levels or to modify rules to generate new games. And in general, these AI engines that are general are supposed to be able to evaluate evaluate all these levels. And they are able to evaluate these levels because the agents that we are interested in are supposed to be able to work on those in this space of games that we are interested in. So we are talking about GVGI here because it's what we work on, but it doesn't necessarily need to be in this particular framework. It could be OpenAI, it could be the ALE framework. The argument for doing it in GVGI is, well, first of all, we're providing several sets, so we have training sets, and every new competition we provide a new set of 10 secret games. So it's a set that is increasing with time, and also it's a way to make a comparison that is valid in order to validate properly the algorithms that are submitted, because all the submissions are tested in games that are not seen before, what allows for a good division between training, validation, and test. And it's something that we can do because we're using VGTL, and we can just create new languages new games with the languages, while other places like ALE, this is quite more complicated or impossible. So if we want to concentrate on the kind of algorithms that have been used during these years in GVGI, I would just only focus on the single player planning track because it's the most prolific mode or track. We have received more than 150 submissions in the last 3 years since the first edition. These here are the rankings of the first edition of the competition, with OLEDs winning the top of the rankings. And then here in this last column, we can see all the different approaches. So you can see things like 3-cert and A-star, Q-learning, some evolutionary algorithms, random, rule-based systems, etc. All this is explained in this reference in case you want to take a look at it. And then from that moment on, from that first 3 certs, that was the best in the first edition, then multiple different methods have been tried. And what I want to show here is how in this algorithm, in this particular framework, many different algorithms have been more or less successful of finding solutions to some of the games, but not all of them. So if we just go through these winning approaches, the first one, OLEDs, which I said is 3 certs, well, it's an open loop spectrum at 3 certs, that's the definition for OLEDs, which uses open loop optimistic planning, and it doesn't use Monte Carlo simulation. So basically, it's a 3 cert method that has been stripped down to its simplicity to be quite efficient. And from that moment on, then the rest of the submissions started to be a little bit more complex, trying to compensate for the fact that there are different types of games. And Jolobot, which is the winner of all the Gecko tracks for some reason, the way it works is quite interesting. It starts with doing pathfinding to the closest sprites around. During that time, using the forward model, tries to identify if the game is deterministic or stochastic. And in case it's deterministic, it uses best first search. And in case it's stochastic, it uses MCTS. And with that, it's been able to win not only some of the legs, but also a few championships, like in a year-based competition. They actually have published a journal paper in TCake about their entry. This has been published less than a month ago. So in case you want to see what's the typical winner of the GVGI competition, you can read it all there. Next year we have other type of entries, but they are also quite similar with respect of the kind of approach that they take. So for instance, here, Return 42, the CIG2017 winner, they use they first determine the algorithm, the game is deterministic or stochastic. After that, they use A-star in case it's deterministic, or random walks in case it's stochastic. YV Creeper, it combines iterative with 3 certs, so it's again 2 different. It's a 3 cert method, but it's also using some reactive avoidance hazards. So it's reactive in a way, and also doing some planning with 3 certs. Mass CTS2, the winner of last year, which is Dennis Summer, and also I think Mark was sort of involved in this. It's using breadth first initialization with some safe preparing based on iterative width, and again with many improvements like progressive history, engram selection, and other things. And these are the winner of approaches. So you can imagine that there are many other approaches which touch different methods and try to combine them in different ways. There is more work on this. We published a paper combining MCDS and evolution and knowledge gathering in the first year, and then other people try to modify MCDS either with macro actions, it's been mentioned before, or with mixed max backups. And the appearance lately of Rolling Horizon algorithms with the work by Enric and Vanessa, and also the work by Raluca this year in 3 different papers about Rolling Horizon evolution, how to modify the algorithm, how to use hybridizations, population seeding parameterizations, etc. So lots of algorithms. We have lots of algorithms, we have lots of games, and here is where the proposal for this vision comes. And the idea is to use taxonomy, is to just take all the games that the general video game AI has, and try to create a classification of games. So this taxonomy is looking like is this tree where all these points are problems, and no, so this is a bunch of problems, and all these points are algorithms. And essentially, they are close to each other if they are very similar in the way the problem behaves. And the vision is to actually do something like this with this. You have several MCTS methods with variants, several Rolling Horizon methods. We could include all kind of simple algorithms. And the idea is to basically cross and see how each one of these algorithms behaves in all the games that we have. So how would you go around and do this? The first thing is just to select a diverse collection of algorithms. So we just select either vanilla versions or all of the ones I've been presenting before. And we basically take a bunch of games and record the performance of these algorithms in all the games. And after doing this, that comes with a matrix. And this matrix is going to have, as columns, algorithms and row games. And this essentially is an agent case embedding. So that's basically a matrix with numbers, and what we can do is convert each one of these numbers or one of these performances that could be a vector into the Euclidean space. So there are points in the Euclidean space. And when you have that, the next thing would be to actually build this tree. This tree is built with the taxonomy, and there are different ways of actually creating this tree. And traditionally, there's been a problem called stability, which is essentially when you have a tree already built, you want to add a new point to the tree completely descompensates. It changes a lot. And the stability actually what it does is to measure how much the tree changes as you keep adding points to this tree. So this tree over here, imagine you add a new problem, and then this it could happen that one of these arms goes completely in the other direction, or many algorithms change center location. So that's been a problem because obviously you want to keep adding games, and your tree should be more or less stable. And the proposal here is to use bubble clustering, which is this new algorithm. And interestingly, this graph, what is shown here is that as you increase the number of dimensions, the stability decreases. So as you have more dimensions in the problem, the number of changes when you add new points basically destroys the stability of the tree. But this bubble clustering, what it does actually is becoming more stable as you keep adding more points or more dimensions. This has been proven in some bioinformatics data. And the bubble clustering algorithm, the way it works is actually quite simple. We have all these points in the Euclidean space that are initialized to some connection strengths of a very, very small value, epsilon. And then randomly, in an iteration method, select bubbles, which are essentially points with a radius, and all the points that are inside those bubbles, what they have is they have the strength. All the pairs of points inside the bubble have their strength make the bigger. So if you have n points, the connection between these pairs is increased by 1 divided by n. And once you have finished a bunch of iterations, using the maximal spanning tree with the connections of all these different points, and it's shown to be quite robust. This is the work done by Amanda Saunders, which is Dan's master student. And apparently she's having the defense in a few, maybe days, so good luck. And the idea is after doing this work with biological data is to move to make 2 games. That's the proposal of the paper. Just to conclude, we say that the no-frills term is not a problem if we determine the generality of the games, if you say that we actually care about this particular case of games. So we don't really want to create agents that play nonsensical games. GVGA is a good framework for this because of the fact that we can keep adding games in theory, forever. The next big goal is actually do what I was describing, just taking all these algorithms, all these games, and create the tree. And then once you have that tree, well, you can diversify, you can specify which tree belong to each groups. We can select, well, Rolling Horizon was very well with this subgroup. Maybe MCTS with this particular enhancement was very well for this one. And then you have some meta heuristic on top of that to decide which game goes to which algorithm. There is also other ways of approaching this, not only by how the games are, but also trying to analyze how the game states are. So how, what the features of the game the games have. So let's say that you're in a particular moment of a game. It's possible that at that particular time, one algorithm works better than another one. And then the game changes because it's doing a completely different thing, moves to a different phase. And at that point, the classification should change and tell you which is the next algorithm to try. Basically, that's work underway, so we'll keep working on this and writing papers about it. And to paraphrase Daniel, we like to send the money, I think he says. Yeah, that's it.
Well, thank you, Diego. Are there any questions for this speaker? You can also ask a question if you haven't done that. Have you worked in hyperheuristics and GVGAI?
Kind of. I don't know. No, I think it makes a lot of sense to cluster stuff based on the algorithm. Because, I mean, in the paper that you also referenced and you're also co-author on, we had these kind of features that we're trying to characterize the games by, but then you introduce a bias because of that, because you just put in your thought of what features work. But I think when you do it with algorithms instead, and especially because there are so many different algorithms that have different kind of characteristics, like we have the hybrids of everything, it might be difficult to identify any kind of patterns because it just might be continuous scale or just like a mixture of everything. So I was wondering whether you thought about that and how to get the features out of this.
Well, in principle, it shouldn't even work with features. So you have all the algorithms, all the games, and then you get the actual classification of them. Now, adding more games to it is the next point. But that's the main idea of having this bubble clustering. So when you keep adding games, the tree doesn't change as much. So what we analyze here, what's used to create the tree, is actually the performance of the agents. So this is completely driven by how the agents do in the game. So in theory, we shouldn't be using we wouldn't be using features, but using basically games and algorithms. That opens the question what to do when you have a game that you haven't played before. Yes, because I knew you were going to put that, but that's something to think about as well, definitely.
Yeah, I also have a question which speaks a bit more to this theoretical part you have earlier. So, I mean, hyperheuristics are really like interesting, exciting approach now. But basically, what you're arguing is like, I mean, the taxonomy you're introducing can't solve the no free lunch theorem. So basically, you're saying in your paper, don't worry about it anyways, and now let's do taxonomies, right? Because if you, I mean, Volpert's results, as you said, are pretty well established now, and then, you know, if you cannot produce a general function that approximates a problem better than average random, then, you know, doing a lot of functions and doing a hyperheuristics over it is not going to solve that either, because, I mean, that would just also be a function approximator with like some selector. I mean, what Daniel Ashlock and you are arguing is basically that games are already a limited domain in a sense by itself, right? Just like how some people argue that there is no you know, people sometimes argue it's futile to go after general artificial intelligence because not even we are general artificial intelligence, because the goals we have are for a very limited subset, and our embodiment gives us a very specific, limited, pre-computed access to the world, and that's why stuff like Markus Hutter's Eixier so might even work, because they're also living in this kind of structured, limited world. I mean, this world is not offering us general problems, just as games are not offering us general problems, right?
Yeah.
Or sorry, it's just more a comment now that I realize, but
Yeah, well, I guess it comes back to the idea of how do you talk about the games that you're interested in. So of course, if you create a very short, so a very small group of games that you want to actually play with any algorithm better than any other one, that would be possible to do with something like one single algorithm. But as soon as you keep adding more and more games, I think that line becomes a little bit blurry, and that's what the taxonomy that we want to work with should come handy in that case.
Okay, are there any other questions? Well, in which case I would suggest we'll thank Diego again for his many talks. And don't go away yet. Julian has some closing remarks he would like to make.
So it's time for the next session. No, no, I'm not gonna say very many words because you don't want to hear me talk, and I don't want to hear me talk. Main thing is that could I ask everyone who's been part of the organization in some way to stand up so I can thank you by name? So Philip, Ahmed, Fernando, Rock, Mike, Christoph, thank you all very, very much. I'd also like to thank, there are some of them out there, all our student volunteers, Noria, Kathy, Kevin, Angela, Hina, Kelly, Jason, Sihao, and Henry. Thank all of you very much. I mean, as usual, these are the people that have done all the work, and some people are not even here. Some people already left, also done a lot of work. And me and Andy have just been saying things. Anyway, I hope you enjoyed it. You will receive an email with a request for slides and some kind of survey with, or like, request for comments essentially. We always like feedback. We'll have to figure out whether we want to do anonymous or non-anonymous.
Remember, feedback is a gift.
Yes, feedback is a gift, unless it has to do with microphones. And I hope to see all of you again, in Maastricht next year, and or somewhere else. So have a great day, and thanks.